Welcome back to ECE 220. This is our last day in Chapter 4. We still have a few chapters to go. If you're reading before you come to class, you might look through Chapter 5. It's dealing with op amps, and we'll start with that tomorrow. Reminder on a lot of the deadlines or deliverables that are in the near future. Saturday, Group A, you need to complete and submit your lab number 2 pre-lab on Saturday. And that's in preparation for your labs, which are next week. On Tuesday of next week, homework number 6 is due, and that will be covering the contents of the material we're finishing up with in Chapter 4 today. We'll be talking about superposition today, and that's the last of Chapter 4, hopefully, that we will be using or working through right now. Group B, you have your split activities going on. Next week you need to turn in your Lab 1 report on Wednesday and your pre-lab for Lab 2 on Saturday. As I started, we are getting into op amps tomorrow, so you might look ahead and read, browse, however you read the material initially for Chapter 5. And as a reminder, which this commercial will continue for another few weeks, please apply for advanced standing if that's appropriate for you in this time in your program process. Superposition. That's what we're going to be talking about, and we're not dealing with Schrodinger's cat or any kind of quantum stuff when you hear superposition that way. We're doing superposition now in electrical and computer engineering in a circuit context, and one of the common ways or times that you will see superposition used is when you have a circuit that has two different sources or multiple sources, and some of those sources might be DC sources, some of those might be AC or alternating sources. We'll look at a example to try to illustrate that to begin with, but superposition in a nutshell is you deactivate all the sources except one of your independent sources and analyze your circuit with that one. Then you do the same thing again. You deactivate all the other independent sources and pull up only one other independent source and analyze your system with it. Because we are dealing with linear circuits, we can do this. That's when superposition applies. And then after you've done all of that, you add all of your results together to get the total voltage or current that you're interested in when all sources are alive or active. We'll look at an example circuit and use the superposition concept to analyze it, and then we'll sort of continue with that same example, but now we'll say, wait a minute, I need to introduce another source. Oh, no problem. Now we just deactivate what we just did, so in a way retain the voltage that we had, but now we introduce one more source and see what it produces to the output, and then add that to what we just found. We'll summarize maybe with what we've tried to talk about today with respect to superposition at the end. Here's an example of applying superposition, and here it's titled a mixed signal circuit. The mixed signal means we have constant sources, and the sources are on the left. They are in series. We have a DC source on top of, it doesn't matter, we could flip those, an AC source. The AC is a sinusoid of 5,000 hertz, and the DC value is 1 volt. The AC amplitude is 1 volt. We're now combining those And that's actually, if you can see it, that's the green waveform. We had an amplitude of 1 on that AC waveform, which means that it should be -1 to +1. But wait a minute, it's going from 0 to 2. Well, that DC source has shifted it or offset it by 1 volt. It's now moved that -1 to +1 AC waveform up, and now this sinusoid is all positive. It's going from 0 to 2. That's our input. We're applying that to this new circuit for us. It now has a capacitor. We're used to seeing resistors. If that capacitor wasn't there, what would we have? If we removed the capacitor, what kind of a circuit would you be working with? Just lump all of those sources into a source box and say, okay, I have a voltage source. What's it seeing? What am I hanging on to that source? You have 2 resistors in series, right? This is drawn maybe a little differently. Maybe you're used to seeing the bottom connected, but it's connected through the same common node. These are all the same. Those are at the same potential. They're at ground. They're our reference voltage. So we do have currents flowing through the circuit, and we have voltages across these devices. But if I simply got rid of that, do you see you just have a voltage divider? Which means, what would the red curve, the output curve, be doing if you just had a voltage divider? Or what would you expect it to be doing? This is lab number 2, which you do next week. You would expect that red curve to be a reduced image, or sort of related to the green curve. And what's going on with the red curve? It is reduced, but now are its peaks aligned with the green peaks? If I now tried to say, okay, here's a maximum on the red, there's a maximum on the green, are they aligned in time? Not anymore, because we have that capacitor. That capacitor is storing energy in its electric field, and so it builds up, then it gives back. It builds up and gives back as you're alternating this voltage across that capacitor. And it can't do that in exact sync with the source, so it's delayed a little bit. There's a phase shift. So when you're doing your phasor transform analysis, you would have a difference in your angle at the end. But here, let's try to make some comments relative to what I've tried to say with respect to this mixed signal circuit. At DC, we will learn that the capacitor impedance is 1 over j omega c. Think of that like a generalized resistor. What happens to omega at DC? What is our frequency omega at DC? How fast are we shaking at DC? We're not shaking at all, are we? 0. So what happens to the impedance of our capacitor at DC? If we divide by 0, what happens? It gets very big, doesn't it, in magnitude? If you just looked at the magnitude of J, what's the magnitude of J? J, remember, is the square root of -1. If we take the magnitude of the square root of -1, or How did we draw J in our two-dimensional complex field? Where did J end up? Wasn't it vertical? How far away was it from the origin? If we walked up vertical to the point J, how far did we walk? What distance did we traverse? 1. So what's the magnitude of J? 1. If we're looking at the magnitude of the complex if we're looking at the magnitude of the impedance of the capacitor, we can neglect that J, and we have 1 over omega C. And at DC, omega is 0. The impedance of the capacitor is infinite. What does that mean that it does in our circuit if we have an infinite impedance presented to the rest of the circuit by that capacitor? When we just have the DC source applied to the circuit, what's the capacitor doing? It's basically not there. Now we can go back to what we've been doing all semester and analyze this circuit as a voltage divider with a DC source. If we just look at the DC source by itself, that's what superposition allows us to do. It allows us to say, let's look at one source first, deactivate all the others, and analyze what's going on. Then put the other source back in and deactivate the first one and look at what happens with the second one. Now add up the contribution of the two and you have the total response. That's what I'm trying to illustrate. You may not understand everything that's going on, but I'm trying to get you to think about when somebody says superposition, oh, he's or they are just taking things one at a time and then adding up the result. That's what we're trying to illustrate. Let me try is the key word here, describe what we're doing. So at DC, the capacitor's impedance is always given as 1 over j omega c, but at DC, when omega is equal to 0, then the capacitor presents infinite impedance. And because of that, so it is an open circuit. And if we wanted to look at what's the output waveform, let's say to DC, then that's going to be whatever these resistors are in a voltage divider circuit. If this is now our voltage that we're interested in, VO, that's our output. Due to DC, this is now 1K over 1K plus 1K times the DC value, which was 1. Or we would expect to have 1/2 of a volt at the output due to the DC input. Is that what we see in this PSpice simulation? We have a 1 volt level where the sinusoid is going back and forth around. That's our input. The red line, where is it going back and forth around? Do you see that it's doing that at 0.5 or 1/2 of a volt? The red curve is doing what we thought it would do at DC. What's it doing when it wiggles? Well, let's see. So now, with AC, alternating current, our frequency of our sine wave in this simulation is actually 5,000 hertz. with AC at a frequency of 5,000 hertz, the capacitor now has a lower impedance than infinity, since our impedance of the capacitor we said was Z sub C is equal to 1 over J omega C. And if we just looked at the magnitude of that, whoops, running out of space, and what was C? C was some, wow, microfarad, which is 10 to the minus 6. And if you go through the numbers, what's the magnitude of J? That's 1. So we don't need to worry about that. We just have numbers in the denominator. We multiply all of that out, and you'll end up with this being about 160 ohms. So as you're shaking at 5,000 hertz in this circuit, you now have an impedance of 1K in parallel with an impedance of 160, or 1,000 in parallel with 160. What's their parallel result? What's their equivalent impedance at 5,000 hertz? Is it closer to 160? Is it closer to 1,000? Is it halfway between? You know how to combine resistors in parallel. You now have 160 in parallel with 1,000. You take 160 times 1,000, divide by 1,000 plus 160, and you get something a little less than 160. Say 140. Now you have a voltage divider circuit in AC where the resistance or impedance at the output is 140, and the other one that it's in series with is 1,000. So now we do a voltage divider of 140 over 1,000 plus 140. We're reducing it quite a bit, and that's why the red curve is much smaller in amplitude than the green curve. So, again, a conclusion. The AC voltage divider yields a much smaller output. If we were looking at VO of AC, now we're looking at something like 140 over 1,000 plus 140 times, and now it had a magnitude of 1 from 0 to peak. Now this ends up being about 0.12. So from peak to peak, we are twice that, and that would be about 0.25. Do you see that this red curve's about maybe about that percentage of the green curve? Hopefully now you did this, let's say, simulation in PSpice, and you go, that sort of makes sense. It seems consistent with my thought process or my thinking. And why are the peaks and valleys no longer aligned between the red curve and the green? Yeah, the green curve input and the red curve output. Why are these maximums and minimums no longer aligned? Do you remember? In Lab 2, are your peaks and valleys aligned? I don't know, I haven't done the pre-lab. It's due Saturday, just letting you know. They are aligned because you have only resistors in your circuit. You don't have these energy storage devices of capacitors or inductors that allow this time delay or phase shift to occur. So this difference here between the maximums is because of this capacitor right there. And that gives us then this energy storage characteristic of the capacitor, which leads to a time delay between when we excite the circuit in the steady state and when it gets in a steady state itself. And sometimes we can translate that time delay into a phase shift. All right, if that was really confusing, so be it. We'll move on. Let's just keep going with superposition. Here's a description. The first thing one of the things you want to take away from this presentation or this period together is that superposition is going to be applied when we have linear circuits. When we have resistors, capacitors, inductors, that's what we're playing with in ECE 220. That's okay for superposition because those provide us with linear circuit elements. Here's a very lengthy paragraph. It's actually one sentence. This is a one-sentence paragraph describing superposition. I will read it to you. Bedtime story. No, sorry I said that. I don't want to put you to sleep. If a circuit contains more than one independent source, that's when you might consider superposition during the analysis process. The voltage or current, it's whatever you're interested in, but let's say we concentrate on one element in that circuit, and that circuit possesses several different independent sources. Then we look at each, or how that circuit element responds to each of the different independent sources, and then we take the algebraic sum of those contributions, and that gives us the total voltage or current associated with that particular element. That's what that sentence is trying to say. In pictures, here's a circuit. We have 5 independent sources, A, B, C, D, and E. Some are voltage sources, some are current sources. If here is the picture of when those particular sources, independent sources, are on, what happens when they're off? If we wanted to turn off source A, how would we turn it off in the circuit to analyze our circuit? What would we do between the nodes of that voltage source A if we wanted to actually turn it off? We'd short it. So now we just replace that source with a short. If we wanted to turn off our current sources, what do we do with those? It's just the opposite. Now we just open it up. We remove it. This is now a short, and this is now an open. Suppose we were interested in computing the current I and the voltage V in this circuit. If we applied the superposition principle or concept, then we would analyze I for these 5 different independent sources separately. What if I wanted to see what the component of I was due simply to source A? Do you see how you could change this circuit? If I just wanted A to be active and I wanted to deactivate all the other sources, what would I do? How would I change this circuit if I just wanted A to be active? What would I do with D? Just short it out. What would I do with C? Short it out. B. Remove it. E. Remove it. What about this one? That's a source, but what's its adjective? Dependent. We can't remove, we have to retain all of our dependent sources. We cannot touch the dependent sources. We leave that in play. The same with the current dependent current source. We leave that activated. But now do you see maybe this circuit might be a little easier to analyze? For what? How the current behaves with just source A active. Question. So now if there was I think the question was if there was a resistor here in this branch, what would happen? Is that the question? What would happen if you now had a resistor in that branch with the current source E? And you're now deactivating E. What happens to that resistor? You can wave goodbye to it as well, right? It's no longer in the circuit, effectively. It's gone because you've opened up that branch. You could find the voltage drop across those 2 nodes, but you don't have any current flowing. Questions on that? What would we do if we wanted B to be active? Do you see how we would change the circuit? Quickly short our voltage sources, erase or remove our current sources, independents, and analyze the circuit. If we think that way, then I sub A is the contribution of the current I when A is active only. I sub B is when B is only the source that's active, etc. So if we wanted I total, we would add all of those contributions up algebraically. Some might be negative, some might be positive. We algebraically add them up and we get the complete or total response of I and V after we've looked at all of these separately. And that's what I'm trying to describe here. I sub A is the current through the current branch I due only to the independent voltage source A. And everything else then is deactivated. And we define I sub B, I sub C, etc. the same way. Question. And we can do the same for V. What happens if now somebody says, you know what, adjust all of those sources, A through E, increase them by 10%. All of them. What's going to happen to I? And here the key is our circuit is linear, so superposition applies. It'll increase 10%. whatever increase means. If I was negative and we increased all of these by 10%, then I would get changed by 10% in a positive direction. And so if it was negative, it would be more negative by a 10% factor. So I increases / decreases, depending on what we did, by the same percentage. Let's start analyzing. Here's a circuit. Let's now solve this circuit using the strategies that we've developed or tried to understand at the beginning of class. And now what I'm going to do is revert back and say, oh, well, let's do it the standard way. Let's just leave them all there, and then we'll check our work. So the first thing we're going to do is we're going to find the answer in the back of the book. We're going to try to analyze this circuit with all the sources active. And what are we trying to find? We're trying to find the voltage dropped across that 10 ohm resistor. And we do have a dependent source. It's kind of weird, but we have a dependent voltage source having a value equal to the current flowing through that 10 ohm resistor. That's our circuit. If we now wanted to analyze that with everything active, are you starting to see a strategy for analyzing that circuit? I know what Nathan wants to do. He wants to do mesh analysis. He sees I see 3 meshes. But let's see if we can see something else. What else might we see? We need V0. Whoops, I'm into highlighting here. But what if we looked at that node A? Here's another node. But if we've chosen this as our reference node, we know what that node is. We know that node voltage. And if we know A's node voltage, if we know I sub 0, we can find that voltage at this point. What I'm suggesting is maybe we try KCL at A, and we have one constraint equation relating our dependent variable I sub 0. What are we going to do with this eventually when we start to analyze this via superposition, which we're not doing initially? But via superposition, how many sources do we have to deal with? There you have to worry about the modifier, modifying sources. We worry about the independent sources. We'll have 3 different sources that we can activate and deactivate. That dependent source, it has to stay. It's retained. So we must retain dependent sources when we get to the point of analyzing this circuit using a superposition concept. All right, we said KCL at A. What does that give us? Suppose we now say, well, let's look at all the currents leaving A. I see a 2 amp leaving A. That's straightforward enough. Now what do I have? Well, I don't know. I'm going to kick that can down the road just a little bit. Let me say that's current going left, I sub L. So I have that one. I'm working my way counterclockwise around A. Now I see 1 amp not leaving. It's coming in, but I'm summing everything leaving, so I'll say that's minus 1. And then I have plus I sub 0, and that's all equal to 0. That's KCL at A. I have a lot of variables there, but I can start to get rid of some of those. What is I sub L? What's the current? That's the same current as this current through that 1 ohm resistor. And if I knew this voltage, I would be able to find the voltage difference between the right volt node and the plus 10 volts and divide that by 1 ohm to get I sub L. And what is that node that I'm pointing to with my symbol? Well, it's a dependent source away from A. And A's value, what's the node voltage at A in terms of really what I'm trying to solve for? Isn't that V sub 0? The voltage at capital A is in fact V sub 0. So if I wanted this, if I said this is V sub x, if I did a KVL, have too many things going on. If I did a KVL around here, I'm sort of doing this on the side. I now have a KVL to try to find V sub x. It's minus V sub x plus I sub 0, that source. But what else do I know about that current source? It's in parallel, isn't it, with V sub 0. So this is now plus V sub 0 is equal to 0. Or that voltage, V sub x, is in fact equal to V sub 0 plus I sub 0. That's the voltage right there. I now take that voltage to find I sub L. I have V sub 0 plus I sub 0 over, minus 10 over 1. That's I sub L. Well, you haven't improved things much at all, but I have replaced I sub L with V sub 0, and V sub 0 I eventually want to find. What's I sub 0? That's Ohm's law, right? I sub 0 is V sub 0 over 10. If I put those things back into my KCL equation, I now have 2 plus V sub 0 plus V sub 0 over 10 minus 10 over 1 minus 1 plus V sub 0 over 10 is equal to 0. Now I have one equation in the V sub 0. You could solve that for V sub 0, and you should find that V sub 0 ends up being 90 over 12, or that boils down to 15 over 2, or 7.5 volts. That's the voltage dropped across that 10 ohm resistor on the right. We now want to analyze this circuit using superposition. So now we have the answer in the back of the book. The answer is now 7.5 volts. Somebody's going, yeah, but I didn't want to do that. Let me just do some 3 simple steps and then add it all together. Let's now deactivate all the sources except for the 2 amp source in that circuit. What does our new circuit look like when we draw it? I'm keeping this one active. I have to retain the dependent source. And what else do I do? What happens when I deactivate the 10 volt voltage source? That's shorted. What happens when I deactivate the 1 amp current source? That I extract or open, and what I'm left with then and to make this distinction, I'm going to call that V sub 0 the first component under this first scenario where the only active independent source is going to be the 2 amp current source. Questions on how that circuit came into existence? That you need to be able to sort of quickly do. This one we should be able to analyze consistently with what we just did. Let me call this node A1 and let me write KCL at node A1. Sometimes you use the same analysis after you deactivate things. Sometimes you'll use different analysis strategies. This now says I have 2 there. And what do I have? Now I need to know the current going there, which is V sub 0, 1 plus I sub 0. That's this voltage minus the reference voltage, which is 0 here, divided by 1. And then I have I sub 0, but I sub 0 is V sub 0, 1 over 10, and that's equal to 0. Where I sub 0 is V sub 0, 1 over 10. This can be used in that. And now I have one equation in the one unknown V sub 0, 1. If you solve that, I'm going to quickly solve that for us and say that this now ends up being minus 5/3 volts. We didn't say everything was going to be positive, and in fact this one now is contributing a negative amount to the overall. That's source number 1, where we deactivated all the sources except the 2 amp source. Let's deactivate another, or let's activate another one. Let's now say we're going to deactivate all the independent sources except, let's say, the 10 volt source. What's our circuit look like now? Actually, it doesn't need to be that tall, because now the 2 amp has been removed, opened up. The 1 amp has been opened up. And we still have our 10 ohm resistor there. This polarity was This is now V sub 0 sub 2. And here's 10 volts. How do you think I want to analyze that one? Probably KVL. This one looks like it's wanting to be analyzed via KVL because I sub 0 is the only current. We have everything in series. We can now write a KVL equation, and we now have minus 10 plus 1 times I sub 0 plus I sub 0, which is our dependent source, voltage source, plus 10 I sub 0 is equal to 0. We can solve for I sub 0, and then we have V sub 0 2 by Ohm's law. This tells us that we have 12 I sub 0 is equal to 10, or I sub 0 is 10 over 12. Therefore, V sub 0 sub 2 is 10 times I sub 0, which is now 100 over 12, or 50 over 6, or 8.33 volts. One more. Now we want to deactivate all of the sources, independent sources. Except now we're going to keep the 1 amp current source. Was the 1 amp? Yeah, it was going in that direction. Here was our I sub 0. Here's I sub 0. This is now plus V sub 0 3. This is 10, that's 1. How might we analyze this? We had quite a bit of luck with applying KCL at that node before. Let's try it again. KCL now at A sub 3. Says we have this current, which is V sub 0 3 plus I sub 0 minus 0 over 1 minus 1 plus V sub 0 3 over 10 is equal to 0. And again, I sub 0 is V sub 0 3 over 10, and we can use that there. We now have V sub 0 3 from the third source to solve for, and if we solve for that, we end up with it being 5-6 volts. Now we are in a position to find or compute the actual voltage when all three sources are present, which the first one gives us V01, the second one gives us V02, and the third one gives us V03. V01 was minus 5/3. V02 was 25 over 3. And V sub 03 was 5/6. You put all of those over a common denominator of 6, and you end up with 45 over 6 which is a little bit bigger than 42 over 6. And in fact, it's 7.5 volts, which is what we expected. That was the answer in the back of the book. We could go on. What could we do now? Humor me for just 30 seconds. What if now I said, okay, we know V sub 0 is 7.5 volts. Now I want to put another source in there. What do? I just deactivate these 3 that are there, put my new one in, and analyze what V0 is with the new one, and add that on to what I had just now found. So superposition allows you to sort of, oh, here I need to do this. Okay, just add it on. Just add it on. Algebraically, but that's what superposition allows. I'll see you tomorrow dealing with op amps.